boldly going where no science show has gone before. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with Helen Scales.
Hello.
With Dave Ansell.
Hi there.
And I'm Chris Smith. Now, coming up this week, why the Boxing Day tsunami wasn't the first of its kind, because now researchers think that it's happened at least 3 times before. When and how, we'll be finding out. Also, how scientists are making molecular music with nanotubes. The result are speakers that are very, very loud, but they're virtually invisible. And also how elephants have learned to avoid roads to avoid poachers. Unfortunately, there's a knock-on problem, and we'll be finding out what that is in just a second. Helen.
Thanks, Chris. This week, it's also our science question and answer show, so we'll be tackling your science questions, including discovering whether cracking your knuckles causes arthritis, why there's no cure for the common cold, and we've all heard about absolute zero, the lowest temperature possible, but is there a maximum or hottest temperature possible?
All intriguing stuff, and that's on the way. Plus, we'll be hearing how an engineering group in Cambridge are grappling with this particularly flighty question.
It's very hard when an aircraft flies over the wind farm to tell which one's an aircraft and which one's a wind turbine, and this uncertainty is an issue to the air traffic controller.
So how have they solved the problem? And indeed they have. We'll be finding out shortly. Dave.
Thanks, Chris. And in this week's Kitchen Science, I'll be demonstrating the principles of pressure and the power of the atmosphere just using 2 drinking glasses. So if you want to have a go, all you need is 2 plastic tumblers, some kitchen paper, some hot water. I'll show you how to do it later.
So that's your opportunity to get all experimental. Thank you, Dave. And that's all on the way. So if you have any science questions, or you just want to say hi, or you want to give us some feedback for the programme, the email address is chris@thenakedscientist.com.
The Naked Scientists Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Now, anyone who watched the images of the Boxing Day tsunami back in 2004 was totally gobsmacked by by what was really the awesome power of nature and the awesome devastation that it unleashed. We all said that at the time this is something which is without precedent. We'd never seen the likes of it before. But now there are 2 papers this week in the journal Nature, back to back. This is Amy Prendergast, who's from Geoscience Australia, and a second group led by Katrin Manika, who's at Kent State University in Ohio. And they've found evidence that, in fact, this isn't at all without precedent. The tsunamis have happened several times in the past, possibly even 3 times. And the way they've done this is to go to Sumatra in one case and Thailand in another case. And they have taken core samples, basically just by drilling down through the surface of marshy areas called swales that are back behind the beach of these coastal regions. And if you imagine 2 ridges which have a U-shaped depression between them, this is where these swales are. And the theory is pretty simple. If you have a big tsunami, it will wash sand and gravel and other deposits over the ridge and deposit it in this swale, in the U-shaped deposit of the marshy area, and it will form a layer there. Over time, this is covered by other debris and material and filled in. And if you take a core sample, you can go back through the timeline and see these layers which correspond to the tsunamis. And because there's organic debris mixed in with that sand and gravel, you can do carbon dating to work out when it happened. And that's exactly what they've done. And they found evidence that there were at least 3 previous massive tsunamis. There was a fairly modestly sized one in 1907, and the fact that this has a historical record to go with it bears out the fact that this is probably a reasonable way to do this study. But then there were 2 surprises. There was another tsunami 700 years ago, and another one 1300 years ago. And these were no mean beasts. The waves that were unleashed on Sumatra were about 35 metres high, and the waves that were unleashed on Thailand in these historical cases were about 20 metres high, so absolutely massive and devastating. And the key question the researchers are saying is, well, what about the people that still live on the beaches in these places today? They have to make a decision between having an easy life and a livelihood, living by the sea, or living safely.
Do we have any idea that it's the same cause of all these different tsunamis? Is it the same area of tectonic trouble, if you like, that's whipping up all these problems time and again throughout history?
One suggests that the answer to that is almost certainly yes, because, of course, the geology is pretty much the same. And when we had the 2004 Boxing Day tsunami, this was about a 1,500-kilometre section of fault line underneath the ocean, which had hundreds of years of pent-up stress, where the fault was the collision of these 2 tectonic plates. They were pressing against each other. They weren't giving. They were just storing energy elastically, and then they suddenly went. And this unleashed a huge amount of energy all at once. We think the same thing's probably been happening time and time again, and this certainly lends credence to that, yeah.
Okay, so now for something slightly different. Now, conventional loudspeakers work by passing a current through a coil that's near a magnet. The current creates its own magnetic field, and so it's pushed or pulled by the magnet. If you keep changing the current, you'll keep moving the coil backwards and forwards. If you attach a cone onto the end of that, that'll move the air. So you create vibrations in the air. With the right set of currents, you can get music. However, as you've probably noticed, if you ever tried to lug one around, loudspeakers are very large, heavy and unwieldy things. Now, Chinese researchers have possibly come up with an alternative. They've produced sheets of roughly aligned 10 nanometre carbon nanotubes. They then applied an electric current to them. And I guess I have a feeling that this was rather a surprise to them. They suddenly found that sound was coming out.
Just to put this in perspective, a nanometre, 10 nanometres, that's about 100,000th of a millimetre across, isn't it? It's absolutely tiny.
Yeah, so they've sort of made a sort of felt out of lots and lots of these nanotubes, lay them down, form a material out of them, pick it up. It's very, very thin, virtually transparent. They were probably quite surprised at the sound coming out of this, because it's not the sort of thing you'd expect. So they had a look at it, they tried to see what was happening, they shone a laser at the surface, and the surface wasn't moving, so that even confused them even more. And what they think's going on is that carbon nanotubes have got a very, very low specific heat capacity, which means it takes very little energy to heat them up. So if you put a current through them, they get very hot very quickly. So the temperature increases up to maybe 80 degrees centigrade. That's going to heat up the air around them. The air gets hot, it expands, and then when the current drops away, they cool down again and the air shrinks again. So you get this vibration in the air because the air's expanding and shrinking and expanding and shrinking. You get sound like this. Now, the advantage of these things is instead of being a big, heavy, unwieldy thing, you just have to make a sheet the same size as you would do a normal speaker. And they're transparent, so you put them in front of an LCD screen on a monitor or an iPod. And because they've got such a low specific heat capacity, they're quite efficient. It's actually not a very new idea. People discovered it over 100 years ago using little platinum foils. The problem is it takes so much energy to heat up and cool down the platinum foil, it's incredibly inefficient. But with these carbon nanotubes, it should be a lot better.
And what are the applications?
Well, if you want to get a nice big speaker on something light, like a mobile phone, then you could just put one of these over the surface of the mobile phone, maybe. Or if you wanted to get a really big one, you could hang it on a piece of glass. Anywhere where you want a big speaker which is light.
And it doesn't take much energy to run it for the reason you've outlined. The amount of heating effect is tiny, and therefore the energy consumption will be low.
It's probably not that much better than a normal speaker, but it's definitely hugely better than the similar ones before.
And now to another heavy, unwieldy, huge thing that creates lots of loud noise, forest elephants, living in West Africa's Congo Basin, which, according to a new study, have learnt to avoid roads, probably because they realise that where there are roads, there are poachers with guns. Now, that's according to the study published in the online journal PLOS ONE this week, led by Stephen Blake from the Wildlife Conservation Society. Now, Blake and his team have shown that by avoiding roads, elephants are confining themselves to smaller and smaller patches of habitat, which could spell even more trouble for this endangered species. Now, they did this by putting 28 collars on these elephants with global positioning tracking systems on them, and essentially followed their movements around the forest in the Congo Basin. And it soon became very clear to them that the elephants were really avoiding the roadways, and even in areas where poachers were kept out, they were nowhere near roads. And in fact, during the entire study, only a single elephant was recorded crossing a road, and when it did, it dashed across about 14 times its normal pace. So we might assume that if these wonderful, intelligent elephants, which we know, they are clever creatures, they've learned to avoid roads and poachers. So maybe this is a good thing because few of them will be shot. But like I said, the real problem is with the current huge increase in road building in areas like this, which is carving up these remaining areas of intact forest and leaving elephants with these really contracting areas of forest, which might not have enough resources and food for them to survive.
So it's actually putting a lot of pressure on those local areas and devastating.
Well, yes, that's one way of looking at it, certainly on the forest, and then, the elephants themselves might not survive. There could be a knock-on effect also on those ecosystems, because it's thought that elephants roaming this large area play a really important role in seed dispersal, and if that's disrupted, then that really could interfere with the functioning of the forests.
And I guess the other problem is that if the elephants aren't moving very far, they're not meeting other elephants, so they could get very inbred if you're not careful.
Absolutely, yes. And the sort of the social aspect and the genetic aspect is something that really could be a problem as well. I think the bit of good news we could look at on this story is that the researchers suggest that maybe some relatively simple and cheap planning measures could be introduced, which could make a real difference for the elephants. So if we really think carefully, the people who can make these decisions about where roads are built, then maybe we can try and minimise just how much these elephants are confined by their fear of roads.
There was a similar but almost opposite finding conducted in Yellowstone Park in the US, where scientists were studying the movement of moose. And they found that moose avoid bears, and because bears avoid roads, because roads mean people and bears are scared of people, the bears avoid the roads, so the mooses have all moved to breed along the roads. But now, unfortunately, the bears are learning that that's where the moose go, and because they want to eat the moose, they're now moving closer to the roads, and this is bringing the bears closer to people, so it's sort of going round and round in circles.
But lots of clever animals out there, that's for sure.
Now, here's another interesting application of technology. Digital cameras are brilliant at looking in one direction, which is normally what you want to do if you're taking a picture of things. You're looking at something, you want to take a picture of that thing. But sometimes you need to see out round the sides as well. Now, the conventional solution to this problem is normally either building a camera which moves around and keeps scanning all the way around you, which is quite heavy and complicated and breaks down a lot, or you use something called a fisheye lens, which is a very, very curved lens. It's almost hemispherical, so it will bend the light in from right at the sides into the camera, so you get it on your camera picture, you get pictures from the sides as well as straight ahead. However, this is quite a big lump of glass and very heavy. Now, insects solve this problem by essentially having thousands of separate lenses, each pointing in different directions, and each one of them produces a single pixel of the image. Now, people have tried to do this, but it's quite difficult to make because you've got to have lots and lots of things pointing in different directions. And because of this, you tend to end up with quite a low resolution image because you can't put in enough pixels. Now, engineers at BAE Systems have built a hybrid solution which uses about 9 lenses pointing in different directions so you get the full view. And then each of those, the light from them is funneled down optic fibres onto a conventional light detector. So you get the advantage of the resolution of a normal image, and you get the advantage of being able to look in all directions you would do a fisheye camera, but it's much, much lighter. You can do it about the size of a sugar cube. And they're looking at putting it on either missiles, because if something is trying to chase something which is moving very quickly, it can end up right to the side of you, so it can still see it and it can't dodge. Or possibly for if you're examining inside body cavities using an endoscope, you want to be able to see the things around the side as well.
That's fantastic. I hadn't thought of the endoscope idea. My mind immediately jumped to shopping centres and anti-shoplifting systems.
As well, yeah.
Because they have to. There are all these blind spots that the thieves work out where they are, where the cameras can't overlap. And if you had a load of those systems that you've just mentioned plumbed in, then that ought to nobble them, shouldn't it?
Maybe you ought to patent it quick.
Maybe I should. Helen.
Well, I'm going to take a step back in time now to a time when the saber-toothed tigers roamed the earth, and with news this week of a study that has suggested that these toothy predators were not lone hunters, but may in fact have lived in packs like many social carnivores do today. Now, that's according to Chris Carbone from the Zoological Society of London and his colleagues writing in the journal Biology Letters this week. And the unusual thing that Carbone and his colleagues did, which I think is really quite clever, was to study modern-day carnivores in Africa to help understand what their ancient ancestors were doing many, many thousands of years ago. Now, there are ancient tar pits in Los Angeles, the Rancho La Brea, I think that's how it's pronounced, which contain the fossilised remains of over 2,000 saber-toothed tigers. And these cats, we think, came to these tar pits to feed on prey that got stuck in this sticky tar, and they all kind of ended up getting tangled up and entombed in this area and fossilised for us to look at. But the researchers wondered whether all these cats came individually to these tar pits or whether they actually arrived together in groups, like prides of lions. And so as a way of investigating this, they played back the recorded sounds of prey animals in distress, both in the Serengeti region of Tanzania and in the Kruger National Park in South Africa. And they were the same sorts of sounds we think that the saber-toothed tigers might have heard thousands of years ago from these wailing prey animals trapped and dying in the tar pits. Now, what they found was that the number of large social carnivores today that were turning up to these recordings was much greater than we would have expected based on the overall population size of these creatures. So around 84% of the animals that came to these speakers were actually lions and hyenas, which are both social animals. Now, the key to the story is that that's weirdly the same proportion of animals at the tar pits in Los Angeles that were both these saber-toothed tigers and something else called the dire wolf, which I think is hinting very strongly that these were also social animals that were roaming around in gangs, which is a much more efficient way of scavenging for food.
It's an amazing thing to think that you can also use indices from today, markers from today, to see what was happening in the past.
Absolutely,
isn't it?
with these wonderful creatures with these huge long teeth that we can't really imagine living today. And exactly, but living in a similar way and doing similar things to creatures still around today. So it's wonderful.
Thank you, Helen. Well, to finish up, there's an amazing sort of, I suppose a concept that every cloud has a silver lining, which is that in the Second World War, towards the end of the Second World War, there was a blockade on part of the Netherlands, which resulted in people being almost starved to death. It was called the winter famine. And people there were surviving on 100 grams of food a day. That's about 500 calories on a good day, which is about 25% of the amount of energy that you or I would need to eat on the average day to keep us just in neutral weight balance. What was the impact of this? Well, obviously people began to starve to death, but there was also another knock-on effect, which was some of those people got pregnant at the same time. And those children that were conceived at that time are still alive today. And so one of the things that's emerged amongst that population is that they have a higher risk of high blood pressure, heart disease, being overweight and having diabetes. But no one actually can explain why. There's just this association between low birth weight and these subsequent life events. And now a group of researchers actually from the Netherlands, this is Bas Heijmans and his colleagues, and they're based at Leiden University, have recruited 60 of those people who were conceived during the Dutch war famine, and they have sequenced their genetic material. So they've examined the DNA, and they've specifically looked at a gene called IGF-2, which is insulin-like growth factor 2. It's a growth factor-associated gene. And in particular, they were interested in looking at something called methylation, because DNA can be controlled, not just by turning genes on and off, like flicking a switch, but also you can control the amount of the expression of a gene by adding chemical groups called methyl groups directly onto the DNA letters. And this acts a bit like a cellular dimmer switch. It can turn genes up and down. And when they studied these people who'd been starved, they found that the number of methyl groups on their DNA was about 5% less than their brothers or sisters who were obviously born in the same family, had the same upbringing, ate the same food, and have largely otherwise been exposed to all the same things as them. And so the only factor they don't share in common, pretty much, is exposure to this famine. And what this elegantly shows is that when you're a baby just developing inside your mother, there's a critical window period when certain genetic tags are set, which will have a knock-on effect in your life for the rest of your life. And so there's this long-term impact. And there are two spin-offs. One of the things that you might say is, well, what can you do about that? Well, the answer is, one, you can guide pregnant women in how to make sure you get plenty of the right sorts of nutrients to make sure this doesn't happen and avoid toxins that could make this happen. But also, because we now understand that this is the case, it might be possible to have tests which you could do on all individuals just to see what the status of the methylation is of various genes in order to see what their lifetime risk is. And who knows, in the future we may also be able to reset that methylation pattern in order to reduce someone's risk of getting various diseases like that.
Is the reason why there might be a mechanism like this because if you're more likely to get diabetes, you'd probably also be more likely to get with all these kind of diseases, you're also more likely to survive a famine. So if you were if you're in a fetus when there's obviously a famine around, there's probably going to be another famine. So there's some mechanism there evolved in order to make you more immune to them.
That's right. So where we've all come from, the genetic legacy we inherited from our cavemen ancestors was that we didn't know where our next meal was coming from. We had lean years when we lived in caves with no food and we all half starved, and then there might be a bumpy year the next year. So it favoured people whose genes told them store energy. The thing is that when you turn up those genes by this sort of process and then live a life where there isn't a shortage of food, such as is the case today, then you see these knock-on genetic effects, so it can have lifelong consequences.
Cool.
This is The Naked Scientist with Dr. Chris, Dr. Dave and Dr. Helen. It's our science phone-in extravaganza, so we're taking your science questions. If you'd like to get in touch with us, the email address for the programme is chris@thenakedscientist.com.
Distilling the best science. The Naked Scientists. For more information, look us up online at nakedscientists.com.
It is The Naked Scientists with Dr. Chris, Dr. Helen and Dr. Dave. We're live on BBC Local Radio right around your part of the region, and we are, of course, live in Second Life because we beam the programme into Second Life every week. And if you'd like to join the group of avatars who assemble at the Naked Scientist Mansion, you go into Second Life, go to the Scilands, which is the science continent, and look for the Naked Scientists. And there's an assembled team of people there who are listening to the programme, and they're also chatting. We've heard from Zanzibar Rothschild, who's listening there, and he says, is there any correlation to earthquakes on the west coast of the US with the tsunami activity in the Pacific? Well, there's some suggestion that if you have big seismic events in one place, that you can get slippage or you can encourage faults to be triggered in other places. But on a global scale, the answer is probably not, because there are thousands of earthquakes happening all around the world all the time. And so by the time the energy reaches an individual fault, the chances are it's probably largely diffused so that it's probably not sufficiently intense to trigger anything. What do you think, Dave?
Yeah, I think it is possible for one earthquake to trigger another earthquake, which probably would have happened in the next year or so anyway, which is just about to break. It's like if you're pulling telling something's just about to slip. So if the earthquake's just about to slip, then one earthquake can trigger another one.
Presumably if it's geographically quite close.
Yeah, I mean, the closer you are, the more likely it's going to happen. But I think there is evidence it can happen the other side of the world, but only on earthquakes which would have happened very soon anyway.
So we've got loads of your fantastic questions for us to answer this week. But first, Dave, what are we going to be doing for this week's Kitchen Science?
Well, this week's Kitchen Science is really, really simple. All you need is 2 similar plastic tumblers, so not the really light, cheapy ones you get out of machines, the ones which pretend to be glass.
You've got lovely kind of like picnic wear there with nice blue spots. That's very nice. OK, great.
You could probably do it with glass ones, but I don't want to tell you to it because you might not have a glass one at the end of it if it goes wrong.
OK, so reach for your picnic hampers, people. Wonderful.
OK, then what you need is some kitchen paper, just normal kitchen paper. Anything a bit absorbent will probably do. So basically get some kitchen paper. You want to cut out a piece about the same size as the top of one of your glasses.
A bit bigger, perhaps? Does it have to go over the edges?
Yeah, you just wanted to go over the edges.
A little bit. OK, right, so you're tearing that. Okie dokie, got that.
OK, then what you want to do is get some hot water, pour it into both glasses. Very hot water out the tap, but it run for a while.
Not from the kettle,
Not
just
from
hot
the
from the
kettle.
tap.
It's a
OK,
bit dangerous.
gotcha.
Yeah. From the tap, pour some into both glasses, give it a good swirl round. Get your piece of kitchen paper damp, put it out, pour the water out of one of them, put the kitchen paper over it, give the other one a swirl, pour the water out, turn it upside down on top of the first one, leave it for 20 seconds, then try and pick it up with the top glass.
Fantastic. That sounds quite simple. I think you should have got that. But basically, get your plastic cups, heat them up with some water, put your piece of kitchen towel on top of them, put them together and see what happens. Going to have Dave back a bit later to tell us how it works.
Thank you, Helen. We are, of course, taking your questions. In a second, Edwin has got an explosive question about bullets falling. But first of all, let's talk to Mattia, who's on the line. Hi, Mattia.
Hey there.
Welcome to The Naked Scientists. Where are you calling from?
I'm calling from San Francisco, California.
Oh, wow. It's early in the day for you.
Yeah, it is.
Well, welcome to The Naked Scientists. What's your question?
My question is, I recently listened to one of your podcasts where you did a story about AIDS and there being a possible vaccine for it based on plant proteins. And one of the questions that intrigued me was, if AIDS hides in our genome, how do AIDS tests that blood banks and other agencies use, how do those work?
Oh, yes, good question. Well, yes, you're right. HIV, when you become infected with HIV, it infects a class of cells that have markers on their surface called CD4 cells, and that can include white blood cells, it can include macrophages, and a whole other class of immune cells. And some of those cells become what's called productively infected. So, in other words, the virus goes in, hijacks the cell, and turns it into a virus factory. But not all cells have that happening in them. In some cells, the virus goes in, it doesn't turn it into an immediate virus factory. What it does is it makes a DNA copy of the virus RNA and integrates that DNA copy, or inserts the DNA copy of the virus genetic material inside your own DNA. And then it just turns off. And so you have cells wandering around in your body which contain HIV, they're infected with HIV, and they can turn on that HIV when they want to, or when the signals are right for that to happen. But to all intents and purposes, they're just a cell going about their daily business. So how do you know that person's got HIV? Well, the tests that we do in the laboratory to detect HIV are what are called serological tests. So one test will look for antibodies, because although people don't seem to become immune to HIV, they nonetheless make huge numbers of antibodies against different parts of the virus. And so we run a blood test in which you take a sample of the patient's blood and you present that blood sample with various proteins which are made synthetically, but they're based on what's on the surface of a virus, and you look for whether antibodies in the patient's blood can bind or lock on to that surface with the viral coat on it. And if that happens, it means that it's a reaction in the test and it goes positive, and we can tell. Another way to do it is if people are just acutely infected, they've only just been infected with HIV, they may not have made any antibodies by that stage, so that sort of test would miss that. So there's also another kind of test which looks instead for virus antigen. So when the virus is growing in cells, it's producing lots of virus proteins which get spat out by cells and they go round in the bloodstream. And so you can do various tests which do the reverse of the test I just described. They have antibodies on the surface of the test plate, and those antibodies grab out of the blood any virus proteins, and so you can then detect that they've been picked up, and that gives you a positive. So there's two ways to do it, and it's all done indirectly by markers. There's a third way, which is actually doing it by DNA tests. So you can take a sample of a patient's blood, and you can then do PCR, polymerase chain reaction, and you can try to amplify or copy virus DNA, and it only copies if the virus is present, and then you can detect how much virus is there, and you can even detect virus that's lurking inside your own genome. So that's basically how it works. Brilliant question. Thanks for phoning in. That's Mattia. I've got a question for you, Dave, which is from Ripu Daman Singh. And he says, wonderful show, I listen to it regularly. Can you conduct electricity up a continuously moving flow of water? We've all heard the idea of someone peeing on the underground and then getting electrocuted. Surely this is true.
You certainly can conduct electricity in a liquid. Whether it's going to move fast enough to overwhelm the flow is basically you need a voltage. If you're trying to make a current flow opposite to the flow of the liquid, you need more voltage in order to get the same current, because there's going to be more resistance because you're fighting. It's effectively moving a lot faster, but you certainly can get an electric current flowing in a moving liquid.
How fast does an electric current flow through a liquid?
Normally in metal it's very slowly, because you've got an awful lot of carriers, so on average it's moving a few millimetres a second.
But the effect is instantaneous, because it's like a Newton's cradle. When you put charge in at one end and it knocks everything along and charge comes out the other end.
So it's moving it, the actual signal is moving it nearly the speed of light, so 0.8 the speed of light. So in a liquid, then yes, you should certainly be able to get a Newton's cradle push along. Might need a little bit more current, more voltage to get the same current there.
And Helen, got a question here from Paul Anderson, who says, when I was a lad I was told that rhubarb stems could be eaten, but the leaves are poisonous. Why is that?
They contain something called oxalic acid, and the reason it's in the leaves, we think, is because it's there to put off predators, well, herbivores really, who come along and munch them, and it's not good for them, and it's not very good for us as well. You would have to eat an awful lot of it to actually kill yourself. The lethal dose, LD50, which is enough to kill off 50% of the rats that are given a dose of 375 milligrams per kilo of rat, is 375 milligrams. And so that would equate in humans to eating around 5 kilograms of leaves, which anyone I think would believe is rather a lot. But yes, it's a problem. It basically acts through your kidneys. This is a compound that actually it sort of interacts with metal ions and can form little crystals, which eventually can trigger things like kidney stones. So that can be a problem. And symptoms include weakness, burning in the throat and mouth, difficulty breathing, abdominal pain, and if you're really unlucky, a coma. So yeah, steer away from those rhubarb leaves, I think, is the answer.
What I want to know is who discovered that you could eat the bit in the middle but not the bit near each end?
Well, so many questions on food. You know, there's the weirdest foods in the world that you would never have imagined. Someone, I think, tries anything.
It's the only answer I can imagine. Thank you, Helen. This is The Naked Scientist, Dr. Chris, Dr. Dave and Dr. Helen. We're taking your science questions. If you'd like to send us any questions or feedback by email, it's chris@thenakedscientist.com.
Lifting the lab coat on the world's best science. The Naked Scientists. For more information, look us up online at nakedscientists.com.
It is The Naked Scientists, and we're talking science questions this week. Let's talk to Edwin. Hi, Edwin.
Hello.
Welcome to The Naked Scientists.
My question is about rifles and bullets. Some scientific friends of mine assured me that a bullet fired from a rifle held horizontally will hit the ground at exactly the same time as a bullet from a rifle held vertically, pointing downwards. Now, fair enough, I'm a linguist, I was rotten at science, but that seems to defy common sense. So can you explain it to me in words of one syllable?
Okay, this is quite a famous... It sounds like a mangling of quite a famous experiment. What the actual thing which they should have told you is that if you fire a rifle horizontally and drop the bullet from the same place at the same time, then they'll both hit the ground at the same moment.
You've got a bullet in one hand, a rifle in the other. You fire the gun at the same moment you let go of the bullet, another bullet from your other hand. The two bullets should actually hit the ground
at exactly the same time. If there's no air resistance, this is basically, again, it's physics. If you imagine there's no air resistance, there's no lift, there's nothing complicating it. Basically, how fast you're going horizontally has absolutely no relationship to how you accelerate downwards. So the bullet which is moving and the one which is stationary will both accelerate downwards at exactly the same speed, so they both hit the ground at the same time. If you take a gun and shoot it straight downwards, then the bullet's going to come out of the end of the gun at several hundred metres per second. second, it's going to hit the ground far quicker than one which you fired horizontally.
We did an amazing experiment at school, which I remember to this day, which shows how good that experiment was, the monkey and hunter experiment, where we had a sort of blowpipe with a piece of tin foil across the end of the blowpipe, which was making an electrical contact to an electromagnet that was holding a tin can at a distance. A ball bearing was put into the glass tube. You blow down the glass tube so that the ball bearing leaves the blowpipe, breaking the piece of foil in the process and therefore cutting off the supply to the electromagnet. So the tin can starts to fall at exactly the same rate as the ball bearing minute that the ball bearing leaves the tube. If all things are equal, i.e. the can is being accelerated down by gravity at the same rate as the ball bearing is being accelerated down by gravity, the two will hit each other. And they always do. And it's called the monkey and hunter experiment because the idea is if a monkey's dangling in the distance on a tree and the person fires the gun, assuming that there's no time taken for the gun discharge to reach the monkey lets go of the tree and starts to drop the same minute the bullet leaves the gun. Therefore, the bullet's falling and the monkey's falling and they should still hit each other. And so it's a very elegant way of explaining that. Thank you, Dave, and a great question. Thank you for that, Cole. Helen, good question here from Rocky Singh for you, who says, huge fan, listen to your programme all the time. What makes underwater animals glow?
Underwater animals glow a lot, in fact, much more than things on land, and that comes down to basically the fact that there isn't any light once you get only not very far down into the sea. So yes, they do tend to glow, and it's a chemical reaction. It happens in all sorts of different ways. Some creatures use a type of bacteria, some just use their own chemicals, which they'll then put together. It's essentially something that a general group of compounds, which we'll call luciferins, which then actually undergo a reaction with an enzyme, catalyses that reaction, and that's called luciferase, turns luciferin into something called oxyluciferin, which at the same time produces light. All sorts of reasons why light is important. It's a good way of communicating in the dark. It's also a good way of sneaking in the dark. I think one of the most clever fish is something called a loose jaw fish, which is a malacostade, and they actually cheat because the first type of light, most of the lights in the ocean that are created by creatures are blue or green, because that is actually the light that can actually be seen down there mostly, because all the red lights get absorbed much earlier, higher up in the water column. But there's this creature called the loose jaw fish, which creates its own red light, which really nothing else can see, because no fish really bother trying to see in the red light range, because there isn't any red light down there. But if you make your own red light and you can see it yourself, then you've got your own kind of secret
spotlight,
sensor,
isn't it? You can go spotlighting
system
underwater.
Yeah, it's absolutely ingenious, because they can see things. The prey thereafter don't know they're being looked at because they have no idea there's red light, and they can see it. So it's really ingenious. And another thing, another one of the glowing marine creatures is the jellyfish. And in fact, this year's Nobel Awards went to three guys, Osamu Shimomura, Martin Chalfie and Roger Stein, who jointly were involved with a thing called the green fluorescent protein, GFP, which I think, Chris, you know all sorts about in terms of the molecular world and understanding what's going on inside us by actually attaching this glowing thing onto parts of anything, really. Look at it under a microscope and you can see what you're looking at. It's a really ingenious thing, which has been recognised by this Nobel Prize.
Yeah, that's right. GFP, green fluorescent protein, it's just a protein that some animals make, but they can grab ultraviolet rays and turn those ultraviolet rays into green light that we can see. So it's a clever protein that's capable of doing that. Yeah. Thanks, Helen. This is The Naked Scientists, and today we're taking your science questions. And still to come, Diana O'Carroll will be here to find out why time goes a bit quicker as you get older. And also Dave is stacking up plastic cups in our kitchen science experiment. Let me just remind you, you take 2 plastic cups, you put some hot water in each one to make the cup hot, swill it round a bit, tip the water out, put a damp piece of kitchen roll between the 2 cups, put one on top of the other, and then watch what happens. But first, before all that, wind turbines. Now, whether you love them or hate them, last year they created over 94 gigawatts of electricity all around the world, and that means they're a useful way to reduce our carbon footprint. But it's large countries like the US and mainland Europe that can really benefit. But the problem is there are location restrictions on where we can put these turbines, because aircraft are not allowed to fly near them, because radar can't tell the difference between a wind turbine and an aeroplane. Bit of a problem for air traffic controllers. Or is it? Because now a company in Cambridge have found a way to solve the problem, and we sent Mira Senthilingam to find out a bit more.
We all know the world is running out of fossil fuels, and that the burning of these fuels is affecting our environment. So we're having to turn to renewable sources of energy, such as wind energy. But the problem associated with building wind farms is that the tall wind turbines that make up the farm are picked up by the radar used by air traffic controllers when they're looking out for planes. and they can't tell if it's a plane or a turbine on the radar system. As a result, these wind farms can't be built where aviation radar is nearby, which severely limits the areas that they can be built. But there could be a solution in the pipeline, thanks to a new technology being developed by engineering firm Cambridge Consultants in the UK. I'm at their headquarters in Cambridgeshire with Craig Webster, Head of Clean Technologies. So Craig, how do the current radar systems work and why can't they tell the difference between planes and turbines?
Currently the radars are designed to search across large areas for air traffic so they can control them. So I think of them a bit like a spotlight where you've got to cover a very wide area. You'd have a very strong narrow beam that you sweep across a wide area periodically, once every 4 seconds that you sweep. And they detect an object, and when an object is moving, they tell when it's moving by the presence of Doppler, which we all understand is when a train goes past and you hear the perceived change in frequency when you get a reflection from a moving object. And when you have movement, you then say, I have an object of interest, which should be an aircraft. But with wind turbines, they're also large objects that are all rotating. They have large structures that look a bit like wings. And unfortunately, what they do is they are seen at random. You have unsynchronized rotation. And maybe it's a little bit like a strobe light, a very slow strobe light. You see different positions of targets, and it's very hard when an aircraft flies over the wind farm to tell which one's an aircraft and which one's a wind turbine. And this uncertainty is an issue to the air traffic controller.
So does the fact that it checks it, say, only every 4 seconds then add to the problem because it could be quite a long amount of time that a plane ends up travelling over a wind farm?
Yes. In some of the examples that we've seen, the air traffic controller loses control of the aircraft for a minute, maybe more. So if there's uncertainty, if they see something that they think might be an aircraft in a wind farm, they have to manage the other traffic in the immediate vicinity appropriately. So they'll put separation distances. Quite often it's a 5-mile separation. And if that wasn't really an aircraft and it was just a wind turbine, well, that causes them some problems. It's a congested air traffic. It uses a lot of fuel. And the converse side of that is if you actually didn't detect an aircraft when there was another aircraft there, that could be a safety situation.
And so what have Cambridge Consultants come up with to try and solve this problem?
Well, what we have is a radar that doesn't scan. So we're able to observe the turbines in a way that we can actually measure the speed of the objects that are moving around, where a scanning radar, the actual long-range air traffic control radars, just don't get the opportunity to dwell on the target for long enough to measure its speed. They can say it's moving, but they can't tell you how fast. And because we can see the speed, we can easily tell the difference. An aircraft moves in a very different way to a wind turbine. If an aircraft is travelling at a speed, say it's 40 metres a second, and it moves 4 metres in 0.1 seconds, because that's the measurement interval that we have, we know that's an aircraft. The wind turbine quite simply doesn't obey the same rules. So it has lots of speed, lots of Doppler coming from the wind turbine blades because they're moving. But they're moving in circles, the tips move faster than the centre, the blades bend and shift as the blades are loaded up. So it gives lots of speed messages but doesn't actually go anywhere.
Now, you say that the main reason it can tell the differences is because it can actually judge the speed at which objects are moving. But how does it actually do that?
It's a bit like the difference between a searchlight and a floodlight. We have what appears maybe a bit like a low-intensity illumination of the entire wind farm, and this is illuminated all the time. So you imagine if you're looking at this visually, you would have time to make the measurements and make the observation. So because we know the speed, we can quite easily discriminate and say we can be certain it's an aircraft and certain it's not a turbine.
So essentially it is simply because you are just constantly watching the area around the turbine?
Yes, exactly.
Where have you tested this so far?
We've tested a small-scale prototype in Norfolk, and that test has shown very, very clear differences between a turbine. Our next test, which we hope to be doing in a few weeks' time, will be to take the same prototype and scale it up a bit so that it's big enough to include aircraft. And we'll be doing aircraft trials within the next few weeks. We feel this is going to be a really positive step for the wind industry to be able to see clear differences, because this has never been done before.
So it might be easier for us to reach our CO2 reduction targets after all. Well, let's hope it works. That was Craig Webster from Cambridge Consultants talking to our Mira St-Thillingham.
Thank you, Helen. It's the Naked Scientists, Dr. Chris, Dr. Dave and Dr. Helen. We're answering your science questions for you. Cole's on the line. Hi, Cole.
Hello.
Welcome to the Naked Scientists. What do you want to talk about?
Well, a friend of mine was getting new tires, and the guy tried to talk him into filling the tires with nitrogen. And I can imagine it might be advantageous to do that on a high-performance racing car, but would it make any difference in a passenger car, and why?
Okay, I think there's possibly a couple of reasons why it might make a subtle difference. One of them is that there's a lot of oxygen in air. That means that's what we breathe, and oxygen's quite bad for rubber. It will cause it to break down and get brittle, basically, and crack. And that's going to reduce the elasticity of the tyre, make it last less long, and make it slightly less efficient. The other thing is that ideally you want a gas inside your tyre which absorbs, if it compresses then expands again, it doesn't absorb any energy. The ideal gases for that is what are called ideal gases. The best ones are monatomic gases, single atoms in them, like
argon, for instance.
Argon,
xenon.
helium.
Helium, that'd be
helium would work. The problem with helium is
yeah.
it'd be quite cheap, but it would escape very easily because it diffuses
very,
through
very
things
small
very
and come through the gaps between the rubber molecules.
Yeah, if you've got diatomic gases, things like oxygen and nitrogen, then that's slightly worse because they take more heat to heat up because they can't just move; they can actually spin as well, which is another way of them absorbing energy. And triatomic gases, things like carbon dioxide and water, can absorb even more energy to heat up, so they're less elastic.
And just on a ridiculously pedantic scale, Dave, isn't the fact that a nitrogen molecule weighs slightly more than an oxygen molecule also worthy of mention? Because, therefore, if you pump just nitrogen into the tyre, the actual gas inside will weigh slightly less.
That will have a minute effect. I mean, I think fundamentally that unless you're doing a huge number of miles and really stressed about the efficiency, increasing the pressure of your tyres slightly more, making sure they're always at the right pressure, is going to have much more effect than filling them with nitrogen.
Thank you, Dave.
We heard from Kenneth by email. He wants to know, why are there only antibiotics for bacteria and none for viruses?
OK, it's a very good question. And the answer is that bacteria are single-celled organisms. They are alive, they are living, and they have a metabolism. Viruses are the ultimate parasites. They're not really alive. They are an infectious bag of genes, which are absolutely tiny. A flu virus, for example, is 1/10,000th of a millimetre across, and they're so tiny that they do not have any of the machinery inside them to make new copies of themselves. They have to infect a cell in order to do that. Now, that means you've got a problem, because bacteria look totally different to our own cells, so it's fairly easy to make drugs and chemicals that will roger a bacterial metabolism and which will not affect our own metabolism. But because viruses have to prey on our own metabolism, they have to use our own cells to make new copies of themselves, it's very, very difficult to find ways to discriminate between the virus and a healthy cell and therefore avoid side effects. Now, there are some drugs that can do that. The most famous is a drug called acyclovir. Most people will know it as Zovirax, which you put on cold sores. And this works because the drug is a special chemical which is activated only in a virally infected cell, because the virus makes an enzyme which locks onto the drug molecule and it switches it on. It will not get switched on in any other cell, and once the drug is switched on, what it does is it forms a special DNA letter which, when the virus incorporates it into its DNA, it cannot make the DNA chain of the virus grow anymore, so it chain terminates the virus and stops the virus growing its own DNA, and that's what stops the virus. But it's very, very difficult to do this. The thing that researchers are now looking at is the possibility of something like RNA interference. This is where you make short pieces of genetic material which are the mirror image of a virus's own genes, and by putting those into the cell, they lock onto the viral genes and make what's called double-stranded RNA, and the cells usually associate this with rubbish, junk or viral infection, and they target them to the cellular equivalent of the waste paper basket and it gets ditched, and that's how you can switch off viruses and cells. And our own immune system uses that strategy sometimes as well. So it's a key problem that we've been grappling with for a long time. That's why we haven't really got a cure for the common cold, I'm afraid.
Thanks for your question, Kenneth. That's right, the living dead, it sounds like viruses are. Very bad indeed.
I've got another quick question here for you, Chris, from John from Corby. He says, are there any health effects from firing off loads and loads of fireworks in a small space?
Well, there would be if you were to breathe in all the smoke, because the way in which fireworks make their nice pretty colours is by exploiting an effect that Bunsen of Bunsen burner fame discovered about 150 years ago, which was the science of spectroscopy. He realised that when you look at something, say a distant star, you can work out what the chemicals are in the star, because different chemicals absorb light and they produce light at specific fingerprint wavelengths, and so you can exploit that fact. If you heat up an element, for example, it will absorb light at one wavelength, it will emit light at one wavelength, so you can get different colours from different chemicals. Each chemical has its own unique so-called flame colour, so you give the element some energy by heating it up in a firework and it glows a certain colour. So to get those nice pretty colours in your fireworks, you have to put lots of metals in. Strontium's a good choice for making red colours. Barium can make nice pretty green colours, so can copper salts, they can make greeny blue colours. So that's how you get the colours. The problem is that all those things can be toxic in big doses. The reassuring thing is that Disney have done some studies where they have Disney World in Florida and Disneyland in California, where they jettison thousands of pounds worth of fireworks on their displays. And over 20 years of doing this, they have never detected any significant heavy metal poisoning in their waters, in the water features where they let the fireworks off. Cynics would say that's because all the people at the fireworks displays have gone home with the heavy metals inside them. But I didn't say that. I just heard it. Anyway, there you go. This is The Naked Scientists, and it's Chris, Dave and Helen, and we're talking and taking your science questions this week. And if you'd like to join in with the programme, the email address is chris@thenakedscientist.com.
From protons to photons and gluons to muons, The Naked Scientists. Science that's fundamentally more fun.
You're listening to The Naked Scientists, and it's time to invite the lovely Diana O'Carroll back into the studio for our question of the week. Hello, Diana. Hello, Helen. Always so nice. I don't know why. Maybe it's the tea. Anyway, this week we've got a clock that's ticking.
Hi, this is Jared from Logan, Utah in the United States of America. Quick question for you. I've noticed that as I've grown older, that time feels like it's moving faster than while I was growing up. I might have thought it was just me, but many other people I know feel the same way, including my mother. Is there any reason for this? And I guess, what is it? Thanks. Love the show.
So, why do our perceptions of time seem to vary so much?
My name is John Weirden. I'm Professor of Psychology at the University of Kiel. Now, the question posed is a simple question, but it has a rather complicated answer, and it's not a thing that's been researched in any great detail, unfortunately. The commonest anecdote seems to be a kind of paradoxical statement about time, where older people report that, for example, the hours seem to drag, but the months pass very quickly. In other words, time seems to pass rather slowly when they're experiencing it, but in retrospect appears to have flashed past. Now, how can this possibly happen? The feeling of time passing, that is, whether time's passing quickly or slowly while you're listening to me, for example, generally seems to be governed by the activities that occupy the time period. If you're watching an exciting film, for example, time seems to pass very quickly. If you're in some very boring situation, it seems to pass very slowly. So when you look backwards over a day, it seems very long if there are a lot of activities, whereas if there are very few activities, particularly very few new activities, it may appear retrospectively very short. So the time paradox in older people, both the slowness of passage of time is experienced as it passes, and the retrospective feeling that it's flashing past may be caused, in fact, by the general tendency for older people to have fewer novel life experiences than they do when they're younger. And that seems to account for both the apparently paradoxical aspects of time experience in aging.
So there's no straight answer to this one, unfortunately. There are two ways of thinking about time. One is how long we think has passed retrospectively, and how fast we think time is passing right now as we experience it. So boring days seem to last forever, and fun ones seem to go quickly, but the more of them we experience, the shorter they appear in hindsight. On our forum, a number of you wrote about the relative amounts of time we experience as we age. So younger people have shorter lives, and relative to that, the same amount of time seems longer. So let's take a look at deeper time now with the next week's question.
Hi, I'm Andy from King's Lynn. I was wondering, if humans were to become extinct, how long before all trace of our existence were to disappear?
So, what would happen to the remains of the human race? If you know the answer, then tell us. Carve it in a stone tablet, engrave it on a metal plate, or just write us on our forum at thenakedscientist.com/forum.
Thank you very much, Diana O'Carroll, with this week's Question of the Week.
You're listening to The Naked Scientist, and this week we're tackling all your questions. We've heard from Karen in the States, and she wants to know, is it bad or not to crack your knuckles?
The answer is that science doesn't really know why you shouldn't. There's no consistent evidence, Helen, that cracking your knuckles, and I can't do it actually. I can occasionally by accident, but do that again? That's disgusting.
I can only do it once. There you go. You got it?
That's just disgusting.
Sorry.
The evidence is that it probably isn't linked to arthritis. It's an urban myth. What's the science behind this? Well, when you actually put your joint under tension, basically you pull on your fingers, you make a negative pressure inside the joint space, and gas that's dissolved in the fluid actually makes the joint expand a little bit. This means that gas comes out of solution. It takes up about 15% or so of the space inside the joint, so the ligaments around the joint pop out making a snapping noise, and you've got this bubble inside your joint now. When you then put the joint back under pressure and squeeze it again, the bubble disappears, cavitating. It releases energy when it does that, so about 7% of the effort that you need to or the energy you'd need to unleash to damage cartilage. So it probably can't damage the cartilage, but it does make some noise, and that's why you hear a second crack when you do this. Evidence actually clinically, or whether or not it's harmful, there was a guy called Daniel Unger who on himself cracked the fingers of his left hand for about 50 years, but not his right hand, and at the end of all this cracking, he had no excess of arthritis in the fingers of his left hand compared with his right. A slightly more objective multi-patient trial was done by a guy called George Castellanos about 10 years ago, and they got 350 patients who were knuckle crackers and for 35 years or so, and they found no evidence of increased arthritis in these individuals, but their joints were a bit weaker. So if you do crack your joints, like you just did, then you probably won't get arthritis, but you might get you might struggle to do up your buttons and undo your jars in future.
I'm afraid I can't avoid it sometimes. I just feel like I have to. But I think also it's now time for us to figure out what was going on in this week's Kitchen Science. So Dave, what are we up to?
Okay, so it's a very simple kitchen science. Just get 2 plastic cups. They don't have to be like the really cheap ones. They're sort of ones which are pretending to be glass, so they're sort of picnic cups, basically. I'm going to put in some hot water into each of them, just out of a hot tap. So into one, and into the other. Now, I've got a piece of kitchen towel. I've cut it to be just so it'll fit over the top of one of these cups. I'm going to wet it in one of the cups. Try not to tear it too badly. Pour the water out of one cup quickly. Put the kitchen towel over the top. Now give the other one a good swirl and pour the water out of it and put it over the top.
So he's turned that one upside down. So there's cups are top to top.
With a nice sandwich of kitchen towel between the two. We've had some speculation while you're doing that, Dave. Zanzibar in Second Life says, as the air cools, suction will end up holding the cups together. That's his prediction. And Crystal Falcon has said, would the paper towel get pulled into one side more than the other?
Well, it's the first one of those two seems very accurate. So, Helen, would you like to do the honours and try and pick this up by the top one?
I'll give it a go. Hopefully I won't break it. Let's have it. So I'm trying to pull up the top one.
Yeah.
And, ta-da! It's coming with it.
It's amazing,
they're stuck together.
Yeah, they're completely stuck. It
Genuinely
doesn't take very
stuck
long
together.
either.
Fantastic.
Try and pull them apart.
Okay, I'm going to pull them apart now. Oh, did you hear that? That was good. It did come, but they did come apart. But there was a sucking sound.
Yeah.
Well, sort of sucking sound. What's going on?
Okay, basically, when you heat up a gas, you give the air molecules more energy. In a gas, the molecules are just little lumps. They're flying around all over the place. If you have them more energy, they're going to fly around the place faster. They can, when they bash into things, they push on them harder, so they push everything outwards, so the gas takes up more space. So when you heated up the air inside these cups, the gas expanded, and some of it fell out, so you got less gas in there to start with. You put the two together, the wet towel is acting as a seal, so no more air can get in there. So as the air then cools down, the pressure drops. So there's more pressure from the atmosphere outside pushing inwards than there is from the air inside pushing outwards. So overall there's a pressure squashing the two together, so they stick together.
Excellent. A little vacuum, I guess. Is that what's going on inside?
It will be, yeah, a slight vacuum inside.
And how does this apply to the real world? I mean, where would we see this applied, or what sort of famous aspect of science is this recreating?
Well, one of the biggest uses for this originally was the first steam engines used the same principle. Basically, what you did is you squirted steam into a cylinder, then that was very big. You then shut the valve, squirted some water in, that caused the steam to shrink. That pulled the piston down the cylinder. It was attached to one of those, a bit like a nodding donkey, the things which use pumps in oil wells. Pulled one end of the beam downwards, pulled the other beam upwards. It was attached to a pump, and it pumped water out of mines.
Brilliant. Thank you very much, Dave and Helen. A very quick question, actually. This is probably the best one for you, Dave, in fact. It's from Hitoshi, who's here from Japan, but he's doing a PhD in entomology, so he's a bug man, over at the University of Georgia. And he says, is there a theoretical maximum temperature? We've heard of absolute zero, but what about the opposite? Is there an absolute maximum?
Well, basically, absolute zero is because temperature is effectively how much energy, very simply, how much energy each individual molecule, each individual, it's a bit smaller than molecule, slightly more complicated than that. Basically, how much energy each molecule's got, each atom in each molecule's got. If you give them more energy, then it gets hotter. If you take energy out, then it gets cooler. Which means that because something can have effectively zero energy, or you can't take any more energy out of it, then you can have a minimum temperature, but you can put in as much energy as you like. It just moves faster, so there isn't really a maximum temperature.
Wow. Well, let's see what happens in the future if anyone manages to get something hot. We know that the temperature inside the sun, of course, is probably about 15 million degrees, and with lasers to create fusion on the surface of Earth, scientists are achieving something in the region of 100 million degrees, so we can certainly get some high temperatures. Well, we're almost out of time, but just time to read this quick email from Michael Burke, who was responding to a question that we raised in the programme a couple of weeks ago, where we had an email from someone who said, is the Earth gaining weight? And I made the point that every year there is the weight of about 2 aircraft carriers worth of debris raining in on Earth from space, so we're gaining weight that way. And Michael Burke has written in to say, also, what about photosynthesis? Because don't forget that E equals mc squared, so E energy equals mass times the speed of light c squared. And since the Earth is being basted in sunlight, plants are soaking up that sunlight and they're using it to drive chemical reactions to create wood and sugars and things, in other words, plant biomass. They're indirectly gaining in weight thanks to the sun, and therefore the Earth is gaining mass that way too. So thanks for pointing that out, Michael. That's all we've got time for this week. I have to say a very big thank you to our wonderful production team, Ben Valsler, Mira Senthalingam and Tom Simpkins. Next week, we're going to be investigating the world of pathology. Is it all about autopsies, murder mysteries and forensics? No is the answer to that one, but it is National Pathology Week, and the Royal College of Pathologists are trying to tell us that there's a lot more to pathology than just a post-mortem. So we'll be hearing about some of the events that are happening throughout this week for National Pathology Week. For instance, we'll be finding out whether home diagnosis is a good idea, and also finding out how pathology is helping to treat diseases like MS, multiple sclerosis. So if you have any questions about pathology, then you can send them in to us, chris@thenakedscientist.com. We'll have the answer for you, hopefully, as well as a whole host of fantastic experiments, as usual, with Kitchen Science. There's more of those on the web, of course, at nakedscientist.com/kitchen science. If you'd like to catch up with any of our previous programmes, they're all on the web at nakedscientist.com/podcast. And don't forget that it's your last chance to win yourself either a signed copy of our new book, Crisp Packet Fireworks, which is our list of kitchen science experiments, or a Naked Scientist t-shirt for one lucky winner. The way in which you can win that is by filling in our survey. That's at nakedscientist.com/survey. Last chance this week, so if you want to have a go, nakedscientist.com/survey. Have a great week, thank you for listening, and see you soon. Goodbye.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.